Hello, my good friends. Greetings to you, RF radio frequency and microwave design engineers, wherever you are. Hope you're having a good time. This is Dr. Mohamed Nezami with another lecture on the design and modeling of RF and microwave communication systems. Today, I'm going to continue with my presentations on the design of low noise amplifiers. We've started with the KU band low noise block. Then we moved on to a KU band block up converter with GaN amplifier system design. We then went into a Ka band block up converter with a GaN amplifier, gas fit pre-driver and GaN amplifiers. And today I'm going to, and then we had another session on a complete front end, transceiver front end for L band iridium, okay, which uses a 10-watt GaN device for a PA. Today, you can refer back to my videos on those. Today, we're going to go into global positioning satellites, okay, receiver front ends. As you know, GPS or global positioning satellite systems are multiple satellites orbiting the Earth, and they all send down signals. And then we have a radio frequency receiver that receives the signals, and it's beyond the scope of this presentation to go into how it determines the altitude, the latitude, and from it can actually figure out geographically where you are on the planet Earth. And it can give you also, it has a time reference. So there's a lot of usage for these receivers, as you have seen, and navigation and time referencing to instruments and communication systems, guidance, and whatever. So what you're looking at here today, I'm gonna go through the design of a dual band L1, L2 designated bands low noise amplifier. And we're gonna start out with an antenna interface hybrid, 90-degree hybrid that basically combines. Right now I've got one terminated input, but normally this input is connected to one polarity, and this one is connected to another polarity of the antenna, as I will show in a minute. And the antenna that I'm going to work with is the one I have designed originally, and there's a video on this. You can refer back to this video. So this is an antenna that has two stacked batches, one batch up on top here, as you can see here, and another one down below here. And so we've got 4 feeds to these, and they're in quadrature. Okay, these feeds actually for the vertical and horizontal vertical on both bands, the L band and the S band. And when we designed this, we initially showed that this is the input impedance or the input S parameters. One thing we do usually is this design in here. I would come in and go to the results and get the solution data, okay, which has the S parameter matrix in here. This is because we're going to take this data, export it so we can load it into ADS or SystemVue in my case right now. So we export this matrix here. We get the format, and then we can do that in there. And in the, so we turn over to SystemVue, and we can do is we get this data and look at it, and we can utilize it into as the impedance of the front end system. We don't drive using 50 ohm. As you can see right now, we're driving this mimicking a 50 ohm device, but instead we don't need 50 ohm. We're gonna make it point to an S parameter file, which has the antenna measurements, okay, both on this side and on this side. So let's put some theory to this. So basically all this is basically we've got 2 antennas, the L1, okay, the L1 1574, and the L2, which is 1200 something. Okay, we basically get both polarizations, the vertical and horizontal, they're 90-degree apart. So we use a quadrature 90-degree hybrid from what used to be Anarin. Now it's ITT or MTT, something. I'll show you the data sheet. And then, of course, we take this signal and we filter it first to reject all the interferences, and then amplify it, and then filter again to reject the interferences and strong nearby components. And then we go into a two-way combiner where we combine the other branch, which is the L2 path. And then we amplify, and finally we go into the final output. Of course, to equalize both sides, I've included this attenuator in here, variable attenuator, which we can set it up using a bipad 3 resistors, so to equalize the paths. Now, what you can see in here, I have a stacked multiple of these filters. These filters are ceramic or SAW devices. So what I did is I used multiples of sources. These are the S parameter files for these filters. And so what I do is I have them in here, and then I switch in and out which ones I want, depending on the service that I want this low noise amplifier to be at. The overall gain of this low noise amplifier is about 37 dBs right now. So when we go into ADS and start doing the actual layout of this, or when we get the layout from Allegro, Cadence Allegro, or Altium, and we go into ADS to do the co-simulations, EM-based co-simulations, we want to allow about 2 dBs of loss for the copper path throughout here. So we're looking at making this as a 35 dB low noise amplifier for GPS. Now, let's put some theory to this. So we're going to talk about the theory of this. So again, like I showed you in here, the hybrid is basically this one here. This is a device. And then we've got these ceramic resonators, filters that we are going to use. These are from mini circuits, as you can see. There's no particular reason to use from someone else. There's CTS. There's a whole bunch of Asian companies that makes these filters. And of course, we have the amplifier device, which is from Triquint or Curvo nowadays. And then we have the two-way combiner, which is from the same company as the 90-degree hybrid, and then amplify again and go. So, like I said, this is Dr. Mohamed Nezami. I'm an independent RF circuit designer. If you have any need for contract out designs, small designs, commercial type designs, I would welcome you to reach out to me. I have a very reasonable rate, either hourly. I would give you an estimate of hours on the design. I take all your specifications, or if you have a legacy product that you want to upgrade or modify, I would take your design files and then work off that and turn into you the complete board with the bill of material, and you assemble it and test it. If you need me to even come in and on site and do testing with you, I will do that as well. So my services is yours. If you like to reach out to me on this number or using this email. I have also a training, a 3-day training. Okay. This is I have one for the Keysight CAD out of microwave design tools, basically the Pathwave SystemVue and the Pathwave advanced design system. In the 3 days, we cover some real world hands-on designs. Also, I have the ANSYS 3D EM modeling training shop, which is you can refer back to my videos on this channel here, and I've got all the videos in there. We cover all the videos, basically all the devices that I did on these videos, passive devices, we go ahead and cover, including the GPS antenna, which I just showed you. I will go through the design with you and have you from zero up, build it and turn in the Gerber file or the DXF file for fabrication. So today's design presentation is on a dual band, dual polarization, global positioning system, low noise amplifier. Okay, and I did show that. Now, just to put some theory, if you survey the GNSS spectrum, we have 5 systems. One of them is not shown in here, which is the Indian system. But we have a Chinese Baidu, we have the US GPS bands, L1 and L2, and we have the Galileo, which is the European band, and then we have GLONASS, which is the Russian band. And they're all really in the L band, either the upper L band or the lower L band. So basically, if you look at this spectrum, it's labeled in starting with an E for Europe, G for GLONASS, and then let's see, L is for the US. Okay, so for instance, if you want to design a system for the US right now, we're mainly interested in the L2 band and L1 band, and that's what I'm going to show today, which is a design that is centered at 1227.6 megahertz or 1.2 gigahertz, and at 1575.42 megahertz or 1.575 megahertz. Okay, the L5 we don't use it. Okay, now you can read more on the use of L5. It's a fairly broadband waveform that is starting to be used in some of the consumer products, but it's beyond the scope of this class of this presentation. But you can read on it. So we're not interested in that band. So if you would design something for the Galileo, you would want to center on these bands here. Basically, the E1 and L1 is similar but wider bandwidth. The L2, we don't have such L2. We have something for the E5, A and B, okay? And then we have the E6, so it's a little bit different. So, and that's why I had all these filters that I did in the design in here. If you see these filters are catering to different bands, okay? But for right now, I'm just basically going to do the US system as an example. So if you are designing a US system, if you are designing a European system, you would want to use ceramic filters or saw filters that coincide, that are centered at these bands. Likewise, if you're trying to do glossiness, you would want to center at these bands. And the most interesting one is they've got the G1 band, the Russian band, which is way up near, almost near the Inmarsat and Globesat bands, okay? But same thing in here, so they've got lower L band bands. Okay, Chinese ones are shown in here as well, so that's another system, but mainly really most of the systems that a lot of people are interested in is the US ones because they dominate very much all the consumer devices that we use in cell phones and smartwatches and other gadgets as well. The thing also to recognize is that we got different waveforms. Most of the waveforms are based on basically code division multiplexing or chipping. Although they're starting to, and they're basically QPSK or BBSK shaped. I know the US is putting a system out that uses continuous phase modulation system. That's still an experimental work, and they're trying to put that up, which is more efficient wave and enables the devices to give you more accuracy. But you can see the bandwidth. That's another concern, that you want to make sure that the bandwidths are all correct for these filters when you choose these filters. And most notably, of course, like I told you at the beginning, the L5 is relatively a wide band. It's plus minus 10.23 megahertz. So that's a 20 megahertz channel, which is a significant increase than the original ones, which just a few megahertz. Okay. Now the Russians, they have the L1 up there with about 4 megahertz bandwidth. Other than that, all these systems are relatively narrow bandwidths. So, well, this one here, the Baidu one is also plus minus 10 megahertz as well, similar to the L5. Okay, commercially, these LNAs. Now, we in a lot of cases, this receiver, this front end of the GPS is a device that is used on top of your car, on top of your vehicle for like agriculture machineries and construction machineries. They would put this on top so that they can get a clear view to the sky. And basically, they're like this. And there's tons of these companies that make these ceramic antennas that have an LNA integrated to them. And that's basically what I'm showing today. Is my design uses this dual band antenna that I designed on HFSS. It's printed. And so what I'm going to do is come in here. Of course, right now for simulation purposes, I have SMA, the coaxial cables feeding the antennas. But in real life, I would have the LNA that I'm designing today laid out here so that you can have, it's just a pin connection between the feed, between the elements and the LNB on the bottom of the board. And it would look something like this, of course. Now, bear with me because my presentation system I'm using, unlike Microsoft, this one, you have to start way at the back if you interrupt it. So we've got these systems where they vary in feeding. They could be like what I have is dual feed, you know, and so what we see here, we see the dual feed for this batch. This is a tinted copper here. This is a ceramic substrate. And this is the lower L2 band, which is smaller, bigger, and smaller and larger bandwidth wavelength, and as you can see in the bottom, and here's the ceramic. The feed for this one, you can't see it because it stops, it's beneath this one here. So some of them are single point feed like this, although most of them are like this, where we take the vertical and horizontal and then combine them in a hybrid, 90-degree hybrid, because we get the horizontal and the vertical, as I show in the vectors in here. So we've got one polarization this way, one polarization this way, and we put them through a hybrid, 90-degree hybrid, which basically will shift this one by 90 degrees and allow it to be sum with this one, and we get an increase in power. So, and in this case, of course, I'm showing, this is out of a paper that I referenced, that I published, and it's referenced in the antenna video. If you go to that video, you can get a copy of this paper, or you can Google my name on ResearchGate, Mohamed Nezami, and you will get a copy of this paper. But this shows you some of these, how some of these commercial LNAs are built. Basically, we get an antenna, a dual antennas like this one here. And then we go into a hybrid like this that combines the signal. And of course, we filter it first, and we amplify, and then filter and amplify. And if you do it this way, of course, if you have any interference, the interference is the outer band is rejected, but the inner band between the lower L band and the upper, the lower L band and the upper L band, if there is any interference nearby or at the edge of the band, that gets amplified and comes in, and of course distorts your signal, and therefore you get less accurate position calculations. These ceramic filters are all surface mount like this type here. So now the other thing, this is just to put a little theory to why we're doing this. What happened when we combine two analog signals that are coherent, okay? We're assuming they're coherent because it's exactly the same signal except rotated 90 degree, and assuming the hybrid does not have any mismatch, phase mismatch and amplitude mismatch, so we're 100% coherent, meaning, okay? And if you do that, the theory said that if you do that, if you look at the signals and you add the voltages, you get twice the voltage, and therefore when you square it, you get 4 times the power, okay, which means it's a 6 dB increase in signal strength in here. However, the noise associated with the feeds, okay, they're assumed to be hopefully equal, but non-coherent, meaning because they're thermal noise and they are completely random in phase and amplitude, and therefore when you combine the noise combines average-wise, and you end up with a square root of something, and that gets you a 3 dB increase only. So the overall increase in power is 3 dB in the signal level when you do this scheme here, where you combine the, it's a polarization combiner, you might say. And that's what they say. So that's the principle why we use the quadrature. You could leave out the quadrature and pick up the signal from one single polarization, but then you lose 3 dB from the available signal to you. So today's LNA that I'm going to present to you, the modeling with the design and modeling using the SystemVue, it uses the dual stack antenna, which I showed you earlier in the HFSS. And we have two quadratures. We split the signal. We go into the upper L1 band and the lower L band, which is the, no, I'm sorry, vice versa. This is the lower L band, and this is the upper L band. And so we've got 1.2 gigahertz and 1.5. So we combine the polarization. We go through a filter, and then we amplify, and then another filter, and then combine them using a Wilkinson surface mount integrated power divider, or power summer in this case. And then we amplify again. And hopefully that when we do that, if you see graphically in here what happened to the interference, it gets eliminated because we're amplifying and filtering separate, so we have more control over the bandwidth to zone in on the bandwidth on the band of the desired signal narrower, so that we reject the out of band. So this is the antenna that I've used, okay? Basically, it's a dual stack printed circuit board. It's not ceramic. Now, this antenna was designed using Arlon material, and I believe it's a 64 mil height substrate, and I chose to design it so that I could design the LNA on the back of this antenna. So that the same board, okay. The design, like I said earlier, is basically as follows. So we take, in this case, I'm not showing both polarization. I'm just showing a single polarization here. But usually you take the signal and rotate it 90 degrees and feed it into here. And that would mimic actually the actual satellite signal coming in. So this is the hybrid 90-degree hybrid combiner. Basically combines this signal and what the signal is coming in here, which is 90-degree out of phase with that signal. And then we go in and hit it with a filter to reject the front end. So usually these filters have a loss of about a dB, at most 1.2 dB. So and then this is about 20 dB amplification on each one of these devices. So you end up with a noise figure always on these LNAs on the order of 1.5 dB to 2 dB at most. Okay. So we do the same thing in here for the L2, and the L2 in here I have as an example many of these filters stacked up. But right now the cross in here shows that it's not simulated, meaning only this one and this one are simulated. These are assumed to be not in the design. And the reason I have them is because I switch them back and forth to utilize, to configure the LNA for various GNSS services like GPS, closeness, Baidu, and the Galileo, okay? And of course, like I said, this is a surface mount Wilkinson divider. You just need a 100 ohm external in here between these two inputs. And so basically this combines the L1 and L2 so that you can go into the GPS demodulator in this case in here. So starting out with this system, well, the first thing we want to do is we want to look at the budget link of starting out at the antenna. You can see how the gain progresses all the way, and we get about 36.5 or 0.6 dB at the L2 band. These are the components that are at the bottom here that are used in this chain. And in this chain, I skipped off the other half, okay? And then we sweep the front end, of course. The front end, we can see that this thing saturates at 21 dBm, and there is no way that we could saturate from a SATCOM signal because we can't reach this high. But our signal is way down here, so it's pretty linear and very good. So we just want to make sure that the front end of both, now the colors correspond to L1 and L2. Now, one of the important things with GPS low noise amplifiers is we want to make sure that the out of band signals don't compress the low noise amplifier. And the way to do this is we sweep the front end with CW, okay, like I'm doing in this case, and measure the compression, okay? And that's basically what's shown in here, that it would take, you know, fictitious 64 dBm to compress on these sides, where in band in here, you can see that the system 1 dB compression point is a minus 16 dBm, okay, which is pretty good. And that's just to assure that the reason we do this is because these ceramic filters, as I will show in a minute, in the modeling tool SystemVue, a lot of them, they have a nice skirt. They pass the desired signal, but then they flare out either below the skirt or above the skirt. So you end up with another band and something out of band, like a 2.4 gigahertz Wi-Fi signal, or some other like commercial radars from airports and so forth, or even land broadcast systems. They can overwhelm the front end and blind the GPS receiver. So that's what we do this, okay? We do the same thing. I did the same thing for L2 band. Same thing we show in here, that it's very clear up to like 2,500 megahertz. So our concern was the Wi-Fi band in here and some other bands as well from the 5G system, just to make sure that it doesn't affect the front end. The frequency response of the front end is pretty nice. This is the overall L1 gain, which is about 30, from 36 to 34, anywhere in there. Same thing for L2 we did. Okay, so it's pretty good, same gain. And this is just showing the both bands with the return loss on both the input and output for all of the corresponding bands. Okay, so this is it. And let's go to the simulator. So this is the simulator, and we start out here. These filters that we have, I have a whole bunch of these filters that we can look at, but essentially what we want to do is we look at the L1 band. As I showed you earlier, you can see that how the gain progresses, and the cumulative gain, how it progresses in the chain up to the point where it gets up to like 36 dB. Now, in the noise figure in this case is 1.4 dB, and of course, I divided that by 2, and that's simply to account for the hybrid combiner, okay? Because in the tool in here, when it calculates the noise figure, it has to include the loss. There is 3 dB loss through this one, but we really don't have a 3 dB. We have a 3 dB of gain in here. So that's what I do is in the let's see, where is it? In the budget link analysis, we have to account for that. So we have to divide the noise figure by let's see, where is budget? Oh, here it is back here. So we have to divide that, the noise figure calculated by 2 to account for that. Now, one thing about SystemVue, when you do a noise figure of multiple input networks like this, it always you really have to disable the other branch. Otherwise, you end up with noise figure that doesn't make sense. So that's what I do is I disable this path here. I terminate this and do the noise figure on this branch only. And when you're ready to do the other side, you do that as well. So few tricks that you have to use for the for the tool, but that's what you have to do. Okay. So this is the L1 band showing the gains, of course, very flat, very nice. The overall system is here showing the L2 and the L1, and we can see the basically return loss is all pretty good. And that's about it. So the rest of the stuff here that I have in here are these filters that are these filters are basically various filters that are commercially available, which I went in and got the S parameters for and started looking at all these filters that you can utilize. And these are either ceramic or SAW filters. So the components I've used, basically, like I said, this is the Anarin. It's a small, tiny hybrid, 90-degree hybrid. It comes in an 0805 package, very tiny. So this is the L1 band. And then another one for the L2 band, basically. The filters I've used are from mini circuits, and you can see they're 50 ohm. Nice ceramic resonators, okay, and they give you all the information. Now, one thing I know I've designed, I spent almost 2 years, part of my job was to design these LNAs, and one of the big things about these is the grounding of these filters. These filters are heavy, they're rigid, and so you really want to follow the instructions on the filter footprint, and then when you come and do the BCB, so you really have to make sure you go into ADS momentum or RFPro, import the BCB and do a EM modeling, or in HFSS, you could do it either way. So this is the other filter, the L1 filter, okay. Like I said, these filters are available from various sources, not just mini circuits. The active device is this device here. Now, you could use a discrete transistor and do matching. You can actually get even better noise figures with that if you use a HEMT device. But this one is a 50 ohm mimic from Curvo, and it's a pretty good device. The noise figure is specified at 0.4 dB of noise figure at these bands. The gain is about 20 dB gain, so it's very good. This device in here, it amplifies up to 6 gigahertz, okay, as you can see here, from 700 megahertz to 6 gigahertz, but there's another system device to this, which is the 9036. Now, that one is only up to like S-band, but it might be a little bit cheaper than this, but I did use this because this gives you a flatter response, because these mimic devices, they tend to have a slope on the gain, as you can see in here. See the gain. So the broader bandwidth the device is the less gain variation you're going to have with it between the L1 and L2 devices. So you want to make sure that is, and that's why I chose to use this device. And this device has a nice feature, which is a shutdown feature. Let's see if the one. So they have a shutdown pin where you can shut it down, and that's nice because the receiver then shuts down the LNA. As you can see here, it is pin 6, so you can shut it down so that you can conserve power. The two-way combiner that I use is this device in here. So, and this one is it can accommodate both the L1 and L2 bands. Okay. So as you can see, we took this antenna design in ANSYS HFSS. We took the S parameters from here, and then we utilize it in the SystemVue design. So this is at the system level right now. Now, where do we go from here? We have to take this. We have two paths to go. Either you can go into ADS and do the whole schematics in there and get a layout and then export it to another schematic using a tool like Altium and Cadence from Allegro from Cadence, because you have to, there are more associated to this. We have like the DC power regulation. DC power that comes in here because the coaxial output coaxial cable, similar to the SATCOM LNBs, the DC comes from the RF output signal. We come in here, we have a duplexer that blocks the DC from going back, and then you get it locally in here. You have to regulate it, and you have to include some ESD protection on these active devices and on the input of the antennas. So you could build the whole system in ADS and then go to the layout. But then I personally would, I'm going to do is go into Altium or Cadence and do the schematics first, do the layout and the precautions that it would take on the filters. I would utilize exactly on all of these components, use exactly what the manufacturer evaluation board, similar footprints, similar layout techniques that they did, because they're the one that made the device, they experimented with it, they know how it works, they know what's best for it. And then I would, again, import the board into HFSS or into RFPro to do post layout EM verification of the system, because we have to put in all the passives in here for the amplifier, for the filters. We might have to include some interstage matching in here, because we have to put this in the ADS now and start looking at the overall slope, gain variations, and noise figure, and then it is very likely that you're going to have to tweak and introduce some interstage, even though SysDAT is 50 ohm, but it's not really 50 ohm for particular tiny little band that you're interested in. So to optimize it, there's still work to do, and that has to be done in ADS. And hopefully the next video series that I'm going to do is on those techniques. So again, I thank you very much for having watched my video. Please, if you don't mind, if you subscribe to my channel, I would appreciate it, and hit the like button so that we can get more appreciated, so that I could continue with these videos. If I don't see that people are watching and are interested, it might discourage me and I would have to stop. So please, I would appreciate if you can spread out the word to come into my site channel and subscribe to me, if you don't mind. Thank you very much and have a great day. Thank you.